Okay. Hi, everybody. In the previous lecture, lecture number 22, I have explained to you some basic information regarding the particle swarm optimization algorithm. I have explained to you how we can initialize a swarm particles and swarm particles velocities. I have also explained some common expressions such as personal best position, personal best fitness, global best position, and global best fitness of the bioswarm. Also, I have explained through examples some examples including the arg minimum function and the enumerate function and the numpy where function, which are very frequently used in bioswarms. Today we continue our discussion in explaining the bioswarms architecture and software based by using Python. And we shall illustrate how to use particle swarm optimization algorithm to minimize Rastrigin function, which was discussed in the previous lecture. We begin with a summary, interesting summary about the basic steps which are usually included within the particle swarm optimization algorithm. First of all, we begin with initialization. This topic was tackled in the previous lecture. Considering the objective function and the domain of the variables of the objective function, we have to initialize the population of the swarm or the particles. And this creation or initialization must be done randomly within the domain. Also, in addition to initialization of the particles, we have to randomly initialize the values of velocities for each particle. This is the first step. The second step is the evaluation, where we usually find the fitness of each particle based on its position. What is meant by that? We mean by that we use the position of each particle, include it in the objective function, and find the value of the objective function, which is called here the fitness. This is a number, a numeric value, which shows to which degree this value is close or far away from the optimum value. After creating the fitness, Now we have an array of fitness values for all the particles. We need to update the personal best for each particle. So we update the personal best position for each particle, of course, based on its fitness value. So after having the fitness, we now can evaluate the personal best position and also the personal best new fitness. Also, we have to update the global best position based on the best position of all particles. Here we compare all the personal best values of the particles, and we select the one which is the best value to be considered as a global best position. We have then to update the velocity and the position of each particle. In order to update the velocity, we normally need to know the current velocity and to know also the personal best position value and the current particle position, and also the global best position value also. With these three values, we can update the velocity according to a well-known formula, which is considered as the bone of this algorithm. The bare bone of this algorithm. We, of course, repeat the activities here, beginning from the second one up to the fifth one continuously until we reach a state which determines the conditions of stopping the algorithm. Usually, we can work with the number of iterations, and when the number of iterations is achieved, we stop the process and see the results. Or we can use the fitness value, the global fitness value of the function, of the objective function, and compare the global best values with each other. And if the difference between them is less than a specific, very small value, we can stop iteration also. Shortly speaking, we can terminate the process if the stopping conditions are met. And as I told you here, usually, in most of cases, we use the maximum number of iterations as a limit, and sometimes we use the error between the last two fitness values achieved by the algorithm. These are the basic steps which are implemented in the particle swarm optimization algorithm. Let us consider this and how it works in a logical form. So, step number one, randomly initiate swarm population of n particles. the number of particles is equal to n. Each particle has a position x, xi. I is the index, which refers to the number of the particle from I equal 1 to n, which is the number of particles. I think this is already known to us as an important step and a beginning step. Also, we have to consider to select the appropriate constants which are used in PSO, such as the acceleration or learning constant C1 and C2, and the inertia constant W. We have talked about these constants. Usually, C1 and C2 are considered between 0 and 2, and W is usually between 0 and 1. Okay. Now we need to iterate, or the process, using two nested for loops in the range of the number of particles n and the maximum of iterations, max iter. So at first we have to compute or update the velocity of each particle. The swarm of I dot velocity here means that the particle with an index I within the swarm, and we are considering its velocity. So the velocity of the swarm I within the swarm is equal to 3 components. The first component really depends on the current velocity of the particle I, swarm of I dot velocity, the velocity of the I particle in the swarm, and this value is multiplied by the inertia W. This is the first term. The second term, it is called the cognitive term, is the result of the product of two constants, R1 and C1. C1, now we know it, we have defined it. R1 is also another constant value randomly selected between 0 and 1. This product will be multiplied by the difference between the personal best position of the ith swarm and the current position of the ith swarm. This is the cognitive term. The social term here is equal to the product of R2, C2. Here also R2 is a randomly selected value between 0 and 1. And C2 is already known to us as a learning coefficient. And the product is multiplied by the difference between the best position of the swarm, the global best of the swarm, and the current swarm position. These three components added together and are assigned to a variable which is called swarm of I velocity. So this is the updated velocity now as it is shown here. Knowing the new velocity in the here, we can find the new position. Updating the velocity makes it possible to find the new updated position of the particle. Usually, the swarm, the I particle of the swarm velocity, which is already found here, is added and equal to the swarm of I position. So the previous position, we will add to the previous position the swarm of I velocity, which already computed. Maybe it is not clear for some of you. I can explain it here downwards. If the current position is x of t, t here is the number of the iteration t, for example, and we want to see the position x at iteration t plus 1, so we add to x of t the updated velocity v of t plus 1. V of t plus 1 really is that velocity which I was talking about just now here. This is swarm of I velocity. This is written here as V of t plus 1, and it is defined exactly the same. It is equal to the current velocity of t multiplied by the weight, the inertial coefficient, plus C1 multiplied by R1. R1 is a random value between 0 and 1. And both are multiplied with the difference between the personal best and the current best. Add to that the social term, which is C2 multiplied by R2. Normally we take R2 and R1 the same, multiplied by the difference between the global best and the current position. So this expression may be easier to understand than it was written here above, but practically they are the same and there is no difference. So, shortly speaking, the first thing we do within the iteration, for each iteration, we first update the velocity, we find the new velocity, and accordingly we find the new position of each particle. Now, an interesting thing also must be included is to take care of the position of the particles so that they all will be within the minimum and maximum values of the bounds of the function. If some of the particles, a swarm of I position, if any particle I of the swarm has a position less than the min maximum, the border, so we assign to it a position equal to minimum x. Minimum x now assigned to swarm of I position. Also the same, if a particle now is more than the bound maximum x, so we assign the value of maximum x to the swarm of I position, to the particle I of the swarm position. By this, we are keeping the particles all the time within the range minimum of x or maximum of x. The last thing we have to do is to update the personal best value of the particle and the global best value of the swarm. And of course, we have consequently to find to update the fitness of each particle and the fitness of the whole swarm. Here we use also, as you see, the following inequalities. If the swarm I fitness, in other words, at first we have to find the fitness, and after finding the fitness of each particle, so for the ith particle fitness of the swarm, if it is less than the best fitness of this particle, so we assign this value to the particle. So swarm of I fitness is assigned as the best fitness. And the position also, swarm of I position is assigned as swarm of I best position. So the best fitness and best positions of the particle are now modified and updated depending on the value of the fitness and the position. The same idea applies for the whole swarm. If the fitness of I particle in the swarm, if we find a particle with a fitness less than the best fitness of the swarm, which is the global fitness, if we have a particle with a fitness less than the global fitness of the swarm, so we will adopt it. So we will take this swarm of I fitness and assign it as the best fitness of the swarm. And also the swarm of I position for this particle will be assigned as the best position of the swarm. This is the logical approach which must be followed up when writing and designing the particle swarm optimization algorithm. Let us try to work with this through an example. This example, as we have said, will minimize the Rastrigin function. So at first, as usual, we imported the libraries which are necessary to work with, and we have defined Rastrigin function. And we consider that this function has two variables and a dimension of equal to x1 and x2. It has only x1 and x2 or x and y. So now we have defined the functions which may be necessary, and we have defined the global function with its dimensions. And now we want to work with the PSO algorithm. So we need, first of all, to define the particle swarm algorithm, def PSO, and for this we shall work with the objective function Rastrigin, the dimension of the objective function, the number of particles, and the number of iterations which is suggested. This is the beginning of definition of the PSO. The function here ends with the return instruction here, which yields the global best position and global best fitness. What does this mean? Global best fitness means that this is the minimum or the optimum minimum value. Some people call it fitness, some people call it the cost. It is the same. So global best fitness means the optimum minimum achieved by the algorithm for the given function. And the global best position is the coordinates also, x and y, where we get the global best fitness or global best score. Now, what is in between? We are going, of course, to manipulate the parameters which are included within the PSO algorithm. As we have said, initially we have to initialize the particles and velocities. This step is usually done for one time only, and it is not updated. So we create an array with random numbers using random uniform. This was explained to you in the previous lecture. And we include here the bounds, the minimum or the lower limit and the upper limit, which are, of course, consistent to our objective function. And we decide the number of particles and the dimension of the array which is going to be created, which really is 2, which represents the x and y positions of each particle. So I have explained to you yesterday that the bounds dot shape of 0, how it comes and how it gives you the dimension of the particles array. Also, now we know how to create the array of velocities, and in order for these velocities to be the same size of the particles array, we use zeros like and pass to this function the particles object here. So at the end here we get an array with zeros with a dimensions equal to the dimensions of the particles. Now this is clear for us. I think there is no difficulties. We have explained it yesterday and now we are repeating it. But one interesting thing, now we need to find the personal best position and the personal best fitness for each particle. But we have these values already created. We have the particles values, the positions I mean here, and the velocities. So there is no more values to compare with. So we are considering them as the best positions or personal best positions and personal best fitnesses. So this object, which is named personal best positions, exactly now at this iteration includes the particles values. So it is n pi copy of particles. They are the same now at this iteration. What is the personal best fitness? It is the values of the positions passed to the objective function where it is evaluated and gives a numbers, and these numbers are the fitnesses, a fitness for each particle. So really it is an array of Rastrigin function, which is the objective function of particle P for P in particles, and for every particle in the particles array we substitute in the Rastrigin function the coordinates of it, and we get a value which represents the personal best fitness. So now, from the particles, we have now particle best positions, which are practically at this iteration the same, and we have new values, particle or personal best fitness for each particle. Now, we need also to find the global best position and the global best fitness on the level of the whole swarm. But now we have an array of particle best positions. This is an array, and there are values. There is a value for each particle which has its position, and we need to select from these particle best positions, we need to select the one which has the minimum value. This will give you the global best position. To do that, we do this with arg minimum. As this value in brackets is an array, so arg minimum will give you the index of the minimum value, which is here. Now, if you put this index in the function p best positions, you will get the value of the fitness or the function. So this is indeed the global best position. In order to find the global best fitness, it is easy. From the personal best fitness array, we have to find the minimum numpy minimum value of personal best fitness. We can find the global best fitness. So what do we have now? We have now 4 new values. The personal best positions. For each particle, we have a best position. The particle best fitness, the global best position, and the global best fitness. Okay. These values now could be used to define or to carry out the update of the velocity, because as I have explained to you above, in order to update the velocity, you need to have the personal best and you need to have the global best values. Now they are given to us. So at first we assign the values of C1 and C2 because we know them. They will be included in the expression of updating the velocities. So C1 is taken as 1.5, C2 1.5. It could be 1 and 1. It depends on the result which you receive. If you receive a result which is a little bit confusing and not so good, so you can manage the values here. You change the values and select the more appropriate. The inertial coefficient W is taken as 0.725. And now we need to update the velocities. We need to update the velocities. So, as we have said before, this is done by using or adding 3 components. The original one, which is the velocities multiplied by the inertia, plus C1 R1. This NP rand value is R1. The rand gives you a value between 0 and 1, multiplied by the difference between the particle personal best positions and the current particles positions, plus C2 R2 multiplied by the global best minus the particles. So we have updated the velocities and we assigned it to a variable called velocities. Knowing the velocities now, we add equal it to particles. We now updated the positions of the particles, as I have explained to you above here. The new velocity in the following iteration is equal, is added to the current position to get an updated value of the position. So this is which is done or shown here. And the last step we shall do now is to update the personal best and the personal best positions and fitness and the global best position and fitness. We create here 2 nested loops, one of them for the positions with the positions of the particles, and this is the iterations. we shall use the fitness. The fitness, as you know, is the Rastrigin function with the particles positions substituted here. So we get a value called the fitness for each particle. Now, if the fitness for any particle, if the fitness for any particle is less than the already existing best personal fitness, so we have to adopt it, and then we take a copy of the position, and this will be the particle best position of the iteration G. And the same thing applies for the fitness, will be also assigned to the particle best fitness for the iteration J. Concerning the updating of the global best, also we compare the fitness value for each particle with the global best fitness. And if it is less, this is good. So we adopt it and take a copy of it and assign it to the global best position. This will be the global best position. And the fitness also will be the global best fitness of the swarm. And at the end, of course, we shall have these variables which represent the global best fitness and the global best position. Now, to run the algorithm here, we have to define the maximum x and lower x here, the bounds between -5 and 5 are acceptable. The number of particles is taken 30. The number of iterations is taken 1,200. And now we shall take our function here, our created function PSO, and take the values of these parameters, assign them. So we put the value of the objective function, which is Rastrigin, the name Rastrigin. This is the bounds of the Rastrigin function. They are known here, the bounds. The number of particles is also known. The number of iterations is also known. Everything is known. So if we run the program now, we will get the output, these two values. The best fitness, the global best fitness, and the best position, which is the coordinates where the best fitness or score takes place. If we print them, we shall have the values as shown here. And as I told you, for this function, Rastrigin function, will have a 0 score always. And you remember the figure I showed you, for any number of dimensions. Here we have taken 2 dimensions, x and y. As you see, if x here now equal to 0 practically, and y is equal to 0, and the score or the fitness is equal to 0. If I want to run it again for you to be sure that it is the case, yes, here it is about 0, here is about 0, and this is about 0. So as you see, the program works, and the PSO algorithm could be used directly without any amendments or developments or enhancements to minimize any objective function. But really, working with the PSO is a little bit more difficult than working, for example, with PySwarms or with PySwarm. And also, as you see here, we haven't the facility to draw or to plot or to animate anything. If we need to do that, we have to add more instructions by using the matplotlib or another library for that. Anyhow, I think that this illustration is useful to you, and if you wish, you can work with it with any other function. In the next lecture, I shall try to minimize the same function by using PySwarms again and by using PySwarm again, and to compare the three results and show you that there is no difference at all concerning the results. And indeed, by using PySwarm or PySwarms, it is much easier, yes, and more compact approach to realize the particle swarm optimization. Okay, thank you very much. Wishing you the best.